Okay, we are now recording. We're going to talk about issues. See if I can get this to where it'll actually look this. If we look at the assignment for this week, Paul here is a sort of, I made a couple of corrections on this, nothing terribly important. Just a couple of minor corrections to that. Michaela, you're going to have to see me to get the correct corrections, but you can print this out and use it anyway. The issue with calculating flow rates. Remember, you will see a question that says that they want to know what the rate of delivery is, the flow rate. And there will be a couple of variants, okay? Flow rate means infusion, which is injection, IV injection over time. IV injection over time. That's what an infusion is. Now, the term infusion can be applied to other situations, but mostly you're going to run into this with an IV, and you've all seen this in the hospital, people hooked up to pumps and bags and other things. Those are infusions. So it's delivering a volume of drug over time. And remember that infusion can be by pump. So this is an automatic device that you can set, and the rate is in milliliters per hour. Or it can be what we call manual, which means there's no pump. You just have a bag hooked up and the drug is dripping into the patient. Now, be aware that the drug first drips into a chamber that's in the IV line, and from the chamber, it goes into the patient. So while it looks like you might be putting air into the patient, you're not. Okay? But there is a chamber that's partially filled with liquid, and the drops are continuous into there, and then the material flows into the arm. And this is in drops. Remember, GTT drop is drops per minute. So the major difference is that you will be told, first off, if it is just what is the infusion rate, and they give you no other information, it's going to be a pump. So right there, you've answered the question, is you're looking for a rate in milliliters per hour. However, if they give you something that says using something like a 15 GTT apparatus, that is going to be using, that will be drops per minute. If you see this abbreviation, or drops, some physicians will use the word drops instead of GTT. But if you see either GTT or drops, then you know right away that you're going to be calculating drops per minute. The calculations are very similar. We're just looking at a different endpoint. Okay? Ultimately, we're going to give, it doesn't matter how we give the patient the drug, whether it's via pump or via a drop rate. But basically, if you see the term drops or GTT, then you know that you're using manual. Otherwise, it's a pump. And the difference here is that we do much the same set of calculations, But the very last step of those calculations, when we're doing the manual delivery, is to calculate the number of drops per minute. Okay. Now, there are lots of ways of giving this. Sometimes we do not need to worry about the formula dV over H. For instance, if you see a medical order that calls for 500 milliliters NS, normal saline. Remember we talked about that. Paul, did you have a chance to look at the video from Tuesday? Yeah. Okay, so you saw that I gave a list of different infusion solutions. Yes. Yeah, great. So 500 milliliters of NS over 8 hours. Okay. Now, I'm going to erase some of this. So they're going to ask, what is the flow rate? Okay. Okay, remember that the flow rate, unless in this kind of a question, it's going to be assumed to be a pump. All right? So the flow rate is milliliters per hour. Well, we have milliliters and we have hours. So this is not a dV over H problem. It's a time problem. Okay, so we have flow rate equals milliliters per hour. So in this case, if we divide 500 milliliters by 8 hours, we're going to get the flow rate. Now, if we divide this out, this is going to be 62.5 milliliters per hour. Now, most of our pumps only can be programmed in milliliter units, not fractions of milliliters. So we would round this off to 63. Okay? We follow normal rounding rules. If we calculate and the first digit after the decimal is 5 or greater, we round up. If it is less than 5, and it doesn't matter if it's 0.49, if the first digit is less than 5, we drop it. Okay, those are the rounding rules.
We drop it to 61?
No, well, no, yeah, we would drop it to, we would simply drop the decimals, and it would be 62. So if this were 62.49 even, it would be 62. But at 62.5, we raise it. We follow those rules pretty clearly. This will slightly shorten the time of the infusion, but only by a few minutes. Remember that in our calculations, if we can come within 10% of the prescribed dose, it's safe for the patient. We strive for much better. 10% is an outside number, and so we don't just get happy with that. We want much better. Now, so those are easy. But let me give you another one where they might confuse you a little on this one. And that might be the prescription. Let me go ahead and erase this. And just say that the medical order is something like 10 milliequivalents of potassium chloride, KCl. K is the chemical abbreviation of potassium, comes from the Latin word for potassium, kalium. And chloride is abbreviated Cl, even though it's spelled CHL. Okay, that's chemistry abbreviations, but that's what you'll see. In 500 milliliters NS over 8 hours. What's the flow rate? And I'm going to be lazy here and just say flow rate question mark. So here's where there's a little information you don't care about. And that information is that very first couple of words, 10 milliequivalents of KCl. Who cares? You're delivering 500 milliliters over 8 hours. So this is the same calculation. Okay. So if we do not have to calculate a dose in some way, if we're given a total amount of drug and a total amount of liquid over a period of time, we just, the volume of the liquid divided by the number of hours. It would still be another 63, because 62 and a half, yeah. It'd still be 63. So again, this is analyzing the question. What do I need to determine? And if we remember this, if we are given a volume and a time, we simply divide. We don't have to do anything more complicated than that. Okay? Now, let's make this a slightly different problem. Okay. Now we have said 10 milliequivalents of potassium chloride in 500 milliliters normal saline over 8 hours using a 60 drop per minute set, an infusion set. Remember, there are 4 basic infusion sets. They will deliver either 10 drops a minute, or per milliliter rather. They will deliver 10 drops per milliliter, 15 drops per milliliter, 20, or 60. I've cheated because I've mentally converted this. I chose 60 because a 60 set because our rate per hour is 63 milliliters per hour. And there are 60 minutes in an hour. That means that we will have a little over 1 milliliter a minute. So anytime you're approximately 1 milliliter a minute or less, you're going to use the 60 drop apparatus to minimize errors. Now, here we've got a couple of things. Now we want to know drops per minute, but we also need to know milliliters per minute, because this means 60 drops per milliliter. So we need to get to drops per minute, but our calculation is going to start off either giving us milliliters per hour, or we might do a slightly different thing here and get milliliters per minute. But we have to get down first to this minute time period. So instead of 500 milliliters per 8 hours, we're going to have 500 milliliters per 8 hours times 60 minutes per hour. Does that make sense? We have to convert to minutes. So if we multiply 8 hours times 60 minutes per hour, it'll be 8 times 60. Okay. Make sense? So what's 8 times 6? Use your calculators. If you don't remember your multiplication tables, that 48, right? So it's 480. So we've got 500 milliliters divided by 480 minutes, and that's going to equal what? Go ahead and do that division. Divided by 480.
It's 1.04.
1 point what?
1.04. So is that like rounding up thing, like still a 5 that's above 5 round up, but if not, leave it at?
No, there's another rule. Never do any rounding other than, you don't want a decimal this long, obviously. Go to at least 2 decimal points, but don't do any rounding until your last calculation. Every rounding introduces some level of error. So we don't round until we've calculated either milliliters per hour or drops per minute. Then we round. And remember, always round drops to whole numbers because you can't count half a drop. Okay. So 1.04, we'll leave it. So now this is milliliters per minute. And now, next rule, when you calculate milliliters per minute, you have to multiply by what we call the drop factor. This number here is a drop factor. And remember, that will be either 10, 15, 20, or 60. And this is all drops per milliliter. Okay, depending on the apparatus you're given. You read it right out of the problem. You will be told which to use. Okay. So we multiply this times 60 GTT per milliliter. Milliliters cancel. So we know that we're going to end up with this. So multiply 60 times 1.04. Pardon?
You said divide 60?
No.
Or
Multiply 1.04 times 60. 62.4 equals 62.4 drops per minute. Now, we cannot count 0.4 of a drop. So we round it. In this case, it's 62 drops per minute. This works. Okay? So we can do that. And people doing this know how to do that counting. Remember, I showed you the apparatus in class on Tuesday, and there's a little dial chamber that you can adjust the flow rate. And nurses and other practitioners who have done this for a while get really good at setting that rate. And then they time it, they check it. You don't just sort of arbitrarily set it and say, oh, that looks right. You have to time it, and they will. So they'll probably time this for, roughly 15 to 30 seconds, count the drops, and then make whatever adjustment they think is needed. Okay. So, that is a little bit more than 1 drop per second. We don't want to, one of the reasons that we use this 60 drop set, which we call the micro set, is when we have small volumes per minute to deliver, because what we don't want is to make errors. For instance, if we decided instead to use the 10 drop per milliliter set, we'd multiply 10 times 1.04 and get 10.4. We'd round that off to 10. Well, we've already introduced a fairly good sized error, because the proportion of taking 0.4 out of 10 is much, much higher than 0.4 out of 62. So we've gotten a larger error. And then if we're off by 1 drop in our count, we've introduced an even bigger error. So we're compounding errors. So we pick and choose the set we're going to use. Most of the time, you'll find that institutions will not have all 4 sets available, and most of your problems will specify 15 or 20 rather than 10. Although if you're delivering a large amount fast, you may use the 10 drop apparatus, but nonetheless, they'll specify. So that's the major difference here. If we are delivering by pump, all of our calculations are in hours. If we are given something that says deliver over the course of 180 minutes, we have to convert that to hours by simply dividing by 60. 180 divided by 60 is 3. 180 minutes is 3 hours. Okay? We should know that. So again, this goes back to reading the problem. Am I doing a pump or am I doing a manual delivery? Okay, that's a major, that's the first question you want to ask. That tells you where you're going. Any journey, and it's a journey to do the calculation, needs to have a defined endpoint to have any use. And the defined endpoint is whether we're using a pump or a manual delivery. If we're using a pump, we can calculate milliliters per hour, no problem. If we're using manual delivery, then we know first off, we're working in minutes. No matter what other information is given, we're working in minutes. And then if we're working in minutes, we know we're going to be calculating first milliliters per minute. Then we know that we're working in the manual because it'll tell us in the problem, it'll tell you which apparatus to use. Okay. Now in the field, you're going to have to make a decision of to which apparatus to use, because you may or may not have a pump. And if you ever, God forbid, have to do something like emergency work, like when they had that major earthquake in Haiti a few years ago, a lot of people went down to work and provide medical care to the people who were affected by that earthquake. And they didn't have electricity to run a pump. So it was all done manually. So they had to sit there and go in with their equipment. And you can bet they took in both micro apparatus and at least one of the other 3. And they would have to make a decision. But that entailed, first off, figuring out how many milliliters per minute had to be delivered to the patient. If it was anything over about 1.1, they'd have to use a larger apparatus. Because larger volumes delivered by 60, you're going to be, drop rates are going to be more than 1 a second. It can very quickly get to be a stream. And then you don't know what you're giving.
Yeah, that's pretty bad.
Yeah. So that's part of the consideration here. So you can deliver up to about 2 milliliters a minute using the 60, because 2 a second is not too bad. But anything above that, can't. You can't. So, first question you ask, what are we doing? Second question, are we just delivering a volume, or are we having to calculate a dose to calculate the volume per hour or minute? Okay, so we'll get to those questions next. But we are past time for our first break, so let's take it. Okay, let's go on. I'd like to throw out another couple of questions. Another couple of ways of looking at things. Okay, there are lots of ways to calculate drugs and drug delivery. One of them is to take an order for a drug that is to be delivered at a specific rate over time. And let's just take a look at a possible drug prescription you could have, and we're just going to call this drug A rather than give it a name, because the name's irrelevant to the calculations, okay? So administer um, 5 milligrams or milligrams per minute. Okay, and we're going to have drug A will be 50 milligrams, will be specified as to be prepared by the pharmacy as 50 milligrams in 250 milliliters D5W. Remember, D5W is 5% dextrose in water, a common infusion solution. It is not at all uncommon for a physician to specify an amount of drug in an amount of infusion solution. These things come in pre-prepared bags, and all we do is pull them off the shelf in the pharmacy and add the drug. Now remember, the drug might have to be reconstituted. We're not going to worry about that in this particular problem, but we just inject it directly into the bag. And as long as the amount of drug that we're injecting is relatively small compared to the total volume of the bag, we ignore the additional volume. So even if we're putting 5 milliliters of this stuff in, we do not suddenly say, okay, our bag is now 255 milliliters. Ignore that. Okay. Now, if we have to inject 100 milliliters into the bag, that's a significant difference, but rarely will you ever see that happen. So, when you see something like 5 milligrams per minute, you know it's an infusion. We don't see a drop rate specified here or a drop apparatus, so we know it's going to be a pump. So our question is, what's the flow rate in milliliters per hour? Okay. So, couple of things. So for use in a pump, we need a dose per hour. That becomes our calculation of D. This is where we have to bring in dV over H, right? Because we're given a drug rate and we're given an amount of drug in a total volume of diluent. So this tells us that we're going to use dV over H as our calculation basis, which means we have to determine what D is and what V and H are. Fortunately, in a problem like this, V and H are known because they're specified. Because this, the 250 milliliters is V and H is the 50 milligrams. So we have that given to us. It's just like reading the label off a bottle in the pharmacy. Okay. Now, if we are given, and a lot of times we will see these given as per minute, doses per minute. If we're given an apparatus, a drop-wise apparatus, that's D. So again, when we're using a pump, D has to be an amount per hour because that's the way the pump delivers. If it's drop-wise, D is an amount per minute. So here, if we're using a pump, we have to convert. So here's another rule. Convert amount per minute to amount per hour. How do we do this? We multiply by 60 minutes per hour. Okay? Simple. Another rule of thumb. When converting a dose per minute to a dose per hour, multiply by 60. So now D now has to become 5 milligrams per minute times 60 minutes per hour. Minutes cancel out and we get 300 milligrams per hour. Okay.
What does that say right there? It says convert something to minutes.
Convert amount per minute to amount per hour. Sorry, I'm lazy. I use abbreviations. So now our calculation becomes D times V over H equals, the D is 300 milligrams per hour. Okay. The V is 250 milliliters. And the hour is, and the H is 50 milligrams. Okay. Now we're going to get a big number here. Remember, we have pumps that can go up to a couple of thousand milliliters per hour. if we do the math here, first off, milligrams are going to cancel, and our answer is going to be milliliters per hour. This turns out to be 1,500. Is that reasonable? Yeah, we can pump that much in. It's going to go in very quickly. It will go in less than an hour, and that's just fine. Now, this is, most of the time you won't see anything like that, but this is the basis for that. What we calculated was the D, what the dose is. Remember that when we are having to do a problem that isn't just a straight volume over time, we have to calculate a dose based on the delivery method. So in this case, we're calculating a dose per hour. That's D. In fusions, we always calculate D as a dose over some period of time. Okay. Now, let's do the same problem, but not use a pump. Let's specify a 15 drop per minute apparatus, okay? So we're going to use 15 They could call it a set. They could call it a venoclysis set. They could say at 15 drops per milliliter. One way or another, you're looking for the key here is if they specify drops and a drop rate of some sort. They look for that. If they don't specify drops or a drop rate, it's going to be a pump. Always. Answer in that way. All right, so in that case, and we'll keep using our rainbow of colors here. In this second case, now let's just forget all of this calculation here. I'm going to erase this. But I'm going to leave up the rules for a pump. And we're going to say that in this case, D is 5 milligrams per minute. Okay? So for the manual, use rate per minute. If the doctor gives you the rate in hours and specifies a drop apparatus, you have to convert hours to minutes and then divide, right? Right? All right, so now V and H are the same. So D is going to be 5 milligrams per minute times 250 milliliters over 50 milligrams. Those cancel out. So 550 goes into this 5 times. And so this is 5 milliliters per minute. Make sense? If you do the math, you'll find out. I did a shortcut. I divided 50 into 250 and you get 5 and multiplied that. I urge you again, go ahead. If you don't feel comfortable doing math in your head, use your calculator. Even if you do feel comfortable doing it in your head, for a while, I want you to use your calculator. Okay? But I often make up these problems so that I can do them in my head. So, because it just takes less time. So now we have to convert, and then we multiply by the drop factor. Remember, the drop factor is whatever they tell you it is. In this case, it's times 15 drops per milliliter. Milliliters cancel. 5 times 15 is 75 drops per minute. So that's what the rate is. And again, our nurses know how to do that. So, make sense to everyone? Yeah. And Paul, I saw you take a picture of the board. Feel free to do that anytime. So that's one of these. There's one more variant I want to throw in. Okay. So let me know when you're finished taking notes. Everybody ready? All right. Now we're going to have a little more fun. Okay. We're going to, let me get rid of this. And we're going to dose by the weight of the patient. There are lots of drugs that are dosed in that fashion. These are usually potent drugs. They're often emergency drugs, but not all of them are that, but they're all pretty potent drugs. So what we have is we're going to dose 5 micrograms per kilogram per minute. Now, last rule of thumb, okay, and it goes into calculating D. We're going to assume that we're going to use a pump here right now. And so we're going to assume we have to convert this to a number of micrograms per hour. Okay. So when dosing by weight, we have to multiply the dose by the kilogram weight of the patient. You will always see this in dosing per kilogram of weight because that is how these drugs are developed and how they're labeled and used. So we have another piece of information that's required here, which is the weight of the patient. Now we can either get that weight in kilograms or we can get it in pounds. But we're going to assume that this is a baby or a child rather. And the patient weight, we need that information. Patient weight equals 33 pounds. So it's a child. Okay. So if the weight is in pounds, we have to convert to kilograms. Remember how we do that? Right, divide by what? How many pounds per kilo? Remember that? Your conversion documents are, you can use those, but I'll just tell you, always have your conversion documents ready, okay? And we do this by divide pounds by 2.2 pounds per kilogram.
See, that's what I thought it was, but I didn't know if that was right or not. I was like, I think it's 2.2 pounds, but I think I might be off.
Yep. Say it. If you're correct, I'll tell you. If you're not, I'll say, well, that's not right, but you at least know that you're dividing. Okay, so again, those conversion rubrics are something you should be keeping at hand until you get them memorized. And they're fairly easy to memorize. You just have to use them enough. We'll tell you, keep going, use those things, refer to them, because anything you do 30 times becomes habit, and you will remember it. Okay, so we're going to divide this by 2.2. So our first step, okay, dose by weight, convert to kilograms. That's one. Okay. The second is multiply times dose per kilogram. Remember that this 5 micrograms is what you would give to a 1 kilogram human. A 1 kilogram human is an extreme premature infant. Remember, a kilogram is 2.2 pounds. That is probably about a 26-week fetus. Yeah. So keep that in mind. That helps you remember that you have to multiply by the weight of the patient, because you're not going to give an adult the dose you give a 26-week preemie. Right? So here, what's 33 divided by 2.2? Okay, 15 kilograms. Okay. In this particular case, okay, so 15 kilograms is now our weight. So we have 5 micrograms per kilogram per minute times 15 kilograms. Kilograms cancel out. 5 times 15 is 75 micrograms per minute. So now we're back to where we were in that first example. We have a dose per minute for that patient. So if we're using a pump, we now have to multiply that by 60, right? Because we need to know now the dose per hour. So in this particular case, you got that, Paul?
Yeah.
Okay. We're going to be now multiplying 75 micrograms per kilogram or per minute times 60 minutes equals minutes per hour. And what is that going to equal, B? You got your calculator out.
Sorry, what is it?
75 micrograms per minute times 60 minutes per hour. So 75 times 60.
4,500?
Right. So that's 4,500 micrograms per hour. And that is D for this problem. So we've gone through a couple of steps. When we're dosing, and often you will see this as some amount per kilogram per minute. When you see this kind of a number, you know, first off, anytime you're dosing by weight, you're going to multiply by the weight. Rule number one, period. Never forget that. If you're using a pump, then the rate per minute gets multiplied by 60. If you're not using a pump, you stop there. And you've calculated D. Right? So now we have, our calculation is going to be, pull out the next rainbow color here,
What is right next to the 75 micrograms? It's like
per
slash
minute,
per minute.
per minute. Sorry. I'm a little sloppy in my handwriting. I apologize.
No, you're okay. I just don't have my glasses on hand, so I can't like see very far. I'm so bad
Okay.
at it.
But yeah, they didn't put me through the Palmer method. I didn't learn how to do all that pretty handwriting stuff when I was a kid.
Yeah, even mine looks like chicken scratch.
Yeah.
sometimes.
Well, these days they don't even teach cursive in school anymore, which
I
just
think they're
drives me
actually
nuts.
starting back up
Oh,
on that again.
good.
Because I read an article about how some of the schools in Fort Collins are gonna start putting like cursive curriculum back in to the mix. So that way everybody kind of like knows how to do that. Cause I feel like a lot of kids don't know how to read it.
Yeah.
They're just like, what?
What is that? Yeah. I was going through some of the papers and stuff that I brought home after my father passed away at Christmas time. I brought back a bunch of papers, and what in there was a letter from my grandmother written to my mother in 1960. And if I couldn't read cursive, there was no way I'd know what she said.
Oh yeah, that's what I think
So-
it's important. I think they should learn it.
Yeah, they stopped teaching it. And there was quite an outcry. A lot of us said, that's stupid. You know, you
I
got to
think
learn
it's
how to
dumb.
use
I'm
it.
even buying my son like cursive books to have at home, just in case if they don't teach it, or at least if like, because a lot of the time too, like I usually write like regular bold print at school, but if I'm doing anything else, I write in cursive.
Yeah,
So my son's not going to be able to read my handwriting unless he knows how to read and write it too.
yeah, you do. You have to be, that's part of literacy. When they took it out, I was absolutely shocked. So anyway, but let's go from there. Now we have D. So we're going to construct D times V over H. And that's going to be 4,500 micrograms per hour times 250 milliliters divided by 50 milligrams. Now, problem. We don't have any way to do this solution because we have the weight of the drug in two different units. So we have to convert. We have to have the same weight units in both D and H. And we have micrograms and milligrams. So we have to convert. My rule of thumb for my personal calculations is to always convert to the smallest unit. In this case, it would be to micrograms. And the reason is that conversion is always a multiplication. Anytime you are converting from a larger unit to a smaller unit, you're multiplying. So, do you remember how many micrograms there are in a milligram? Do you have your conversion rubric stuff with you? Aha, you need to carry it until you get it memorized. Okay. Yoko, do you remember?
What was the conversion for it?
Yeah,
It was
conversion of how many micrograms per milligram?
Just looked it over yesterday. I can't remember off the top of my head. I did look at it yesterday though, because I was doing something that had to do with.
Go ahead, B, you're looking it up. It's 1,000, yeah. Yeah, remember, in medicine, the metric units are, in terms of weight, are always in blocks of 1,000. So we've got a gram, which is composed of 1,000 milligrams, and the milligrams are each composed of 1,000 micrograms. We don't go any smaller than that. Okay? And in terms of dosing, we don't go any higher than that. Any higher than a gram. Okay, so now we have to multiply. Always, anytime you have different weight units, you have to convert. Okay, so we're going to multiply 50 times 1,000 micrograms per milligram. Milligrams cancel, and what we have is 4,500 micrograms per hour times 250 milliliters divided by 50,000 micrograms. Micrograms are going to cancel out. So here's where your calculator comes in useful. I see you have it already out. B, go ahead.
So it would be, I would divide
4,500 times 250 divided by 50,000. .5 milliliters per hour. Obviously, we round that off to 23. So, all those great big numbers became a little number, right? So remember, don't get scared by big numbers. They're just numbers. So that is the number of milliliters per hour that this patient is going to receive. Note we didn't put any time limit on it. When we're dosing at rates like this, so many micrograms per hour or micrograms per kilo per hour or per minute, so many micrograms per minute or whatever. They're just numbers. We just use the numbers. But you see that in some cases we have to use some logic and change those numbers. But it all boils down to the important thing to do. All of what we've done, the last conversion of milligrams to micrograms was just a mechanical issue with trying to solve the problem. The real key is we have to calculate D. We're often given all the information we need for V and H. And we should be given the information we need for V and H. Okay? Questions? Okay, it's time for our second break. So let's take a quick break and then come back and we will do the in-class activity. I have a worksheet for you. Okay. And it looks long. I'm only going to pick out a few problems I want you to work on.
And all of those are gonna be pretty much what we've been going over.
What we've been going over. Yeah, great,
This will be good. Definitely
great.
practice. I haven't had math since high school, so.
Yeah, that's not uncommon. You
Yeah,
know.
it's not hard. It just like math like just sucks. I don't like numbers. They change at a constant rate and always something different with them, and that's kind of like a struggle for me. I like when things are like consistent, you know what I mean, and stay at the same pace rather than like always changing up. Because then I feel like I'll scatterbrained after.
Well, I think, you know, look at each problem as isolated. The numbers aren't going to change in the problem. You're going to change them with some of these steps we have to take. But you'll have everything you need to answer it, along with the knowledge you have, like conversion rates from pounds to kilos, like conversion rates from milligrams to micrograms or milligrams to grams or whatever. You'll have all those either in your head or it'll be written into the problem. They will give you everything you need to solve it. The key always with word problems is what's the important information we have. Okay, and you'll find that you probably have plenty of information here, excuse me, to do everything that's in the homework assignment and in the assessment. Okay. Okay, so while you're taking a break, I'll pick out which of these problems I want you to use. I've been looking at them and trying to figure out which ones I like, because some of them are totally off the wall. Okay, so Taylor and Michaela, I'm going to cut this off at this point. If you have questions, you can email me. And I'd like you to be sure that you watch this this video and let me know that you've watched it by sending me an email with a code word in it that will be Swansea, SWANSEA. Hope to see you in class on Tuesday.